Okay, in our last class, we graphed y equals x squared plus 3, and then we found its inverse by switching the x and y points. I want to do that again today, but just do it with the parent function, the parent quadratic y equals x squared. So the x values will be negative 2, negative 1, 0, 1, 2, and these give us 4, 1, 0, 1, and 4. And I'll graph those over here. And we, of course, get this parabola. Now, to find an inverse of a function, we switch x and y. So ignore this for a second. Pretend like that's not there. To switch x and y, we'd have 4, negative 2, 1, negative 1, 0, 0, 1, 1, and 2, 4. 4, 2. That's going to graph over here, and I'll do it in red. Like this. This still forms a parabola, but it's a parabola that's on its side. Going kind of like this. Now, you might notice this graph, this red graph, the parabola on its side, isn't a function. It's not passing the vertical line test. The reason it's not passing the vertical line test is because the original function didn't pass the horizontal line test. So if a function doesn't pass the horizontal line test, that means that if it's not a one-to-one function, if it's not a one-to-one function, then its inverse won't be a function at all. It's an important thing to understand. So this is the line y equals x. Okay, every inverse is a reflection over the line y equals x. So any line that was pointed this way gets reflected and now points this way. We fail the vertical line test. So even though the inverse of a square isn't a perfect function, we find some way to make it work. What we do is we say, okay, let's just take half the graph. Let's ignore all the stuff that isn't working, and we'll just call this the square root of x. And the square root of x is what gets us our function. So we could really split into two pieces. We have the positive square root of x and the negative square root of x, and we just graph the positive. The positive root forms this half parabola here, pointing off to the side. So just to recap a couple things here, if the function isn't one-to-one, its inverse isn't going to be a function. And another way of saying this is if a function doesn't pass the horizontal line test, its inverse won't pass the vertical line test. The way that I get smart about this is I take x plus 5, and I want x plus 5 to come out to 0, 1, 4, and 9. I picked those numbers because they're the first 4 perfect squares. So if I can make x plus 5 equals 0, 1, 4, or 9, then my square rooting gets a lot easier. So I actually set up 4 equations. X plus 5 equals 0, x plus 5 equals 1, x plus 5 equals 4, and x plus 5 equals 9. And I solve those 4 equations, subtract 5 a whole bunch of times, 8 times. I'll get x equals negative 5, x equals negative 4, x equals negative 1, and x equals 4. These are the numbers I should be plugging in for x. Negative 5, negative 4, 1, 4. I don't know why that wrote so poorly. Negative 5, negative 4, 1, 4. Now, these are just the numbers I'm going to plug in for x. I still have to go through the process of doing that. If I plug negative 5 in for x, negative 5 plus 5 is 0. The square root of 0 is 0. This is the point negative 5, 0. I plug in negative 4 for x. Negative 4 plus 5 is 1. The square root of 1 is 1. I plug in negative 1 for x, I'm going to get out 2. And I plug in 4 for x, and I get out 3. Here is my half parabola on its side. I'm going to plug in smart numbers for x to make the calculations and computations and graphing with whole numbers, or at least integers, rather simple. So in this problem over here, I want x minus 2, let's go in purple. I want x minus 2 to come out to the numbers 0, 1, 4, and 9. So I add 2 to all of those. And I get 2, 3, 6, 11. 2, 3, 6, and 11 are the numbers I'm going to plug in for x. 11 is going to be too big for me to fit onto this graph. That'll happen with 9s sometimes. Don't worry about that. So now we have to actually go through the process. Plug in 2. 2 minus 2 is 0. The square root of 0 is 0. Negative 0 plus 3 is 3. Plug in 3. 3 minus 2 is 1. The square root of 1 is 1. Negative 1 plus 3 is 2. Let's plug in 6. 6 minus 2 is 4. The square root of 4 is 2. Negative 2 plus 3 is 1. And 11. 11 minus 2 is 9. Root 9 is 3. Negative 3 plus 3 is 6. So I have the point 2, 3. 3, 2. 6, 1. And then 11, 9 would be like way out. Or sorry, 11, 6 would be like way out here. 11, 6 is incorrect, sorry. 11 minus 2 is 9. Root 9 is 3. Negative 3 plus 3 is 0. This should be 11, 0. This graph goes kind of like this. This one's going down because the number in front was negative. Now, you'll notice these graphs have a starting point. The domain isn't going to be all real numbers. The domain is going from x is in the set 2 to infinity, and the range, y, is an element of 3 to negative infinity, or I'll say negative infinity to 3. And that too should have been bracketed. The good news is, all of these graphs are going to follow a predictable pattern. The only issue becomes knowing what you should plug in for x. So I'm going to take the numbers 0, 1, 4, and 9 and add 4 to them all. Why do I add 4? Because that's the inverse of subtracting 4, right? We want x minus 4 to equal 0, 1, 4, and 9. To make that happen, x has to be 4 numbers bigger than 0, 1, 4, and 9. We add 4 to both sides, so x has to be 4, 5, 8, and 13. Again, I can't fit 13 on my graph unless I scoot everything over, which, you know, you're free to do. And that'll happen sometimes. So, plug in a 4, 0, negative 2. We plug in a 5, 1, negative 1 half minus 2 is negative 2.5. The next one's going to be negative 3. The next one's negative 3.5. You might be wondering how I got those numbers so fast. I'm going to just keep showing you patterns little by little. Here's the next really helpful pattern. This number is how this changes if you picked these correctly. If you picked the correct smart inputs, the outputs will change by whatever your A value is. So, 4, negative 2, 5, let's just take this graph and slide it over. I'm going to give myself some more space to work with. Move all this over here. 4, negative 2, 5, negative 2.5, 8, negative 3, 13, negative 3.5. About here, probably. Domain is the set of all x such that x is greater than 4, greater than or equal to. Range is the set of all y such that y is less than or equal to negative 2. I don't care if you use interval notation, which I did last time, or set notation, which I did this time. But let's formalize all these patterns. Square root functions do what every other function does. A, h, and k. A dilates it and reflects it. H moves it left to right. K moves it up and down. Now I'm going to go through this quickly. So if you're watching this video for the first time, there's another video you could link to that explains in really great detail what A, H, and K do. But for most of us in the class, this is like our 5th time seeing this, so we should start to get a clear understanding. If A is greater than 1, the graph increases faster. So like here's your parent function. Your parent function is y equals the square root of x. If A is greater than 1, the graph goes up faster. If A is less than 1, the graph goes slower. If A is positive, the graph goes up. If A is negative, the graph goes down. And then H and K is your starting point, as I call it. The starting point is like the first point of your graph, where everything is being graphed from, is going to be the point H, comma, K. That's what this was saying. You take the opposite of H, but it's at H, comma, K. The domain is x is greater than H, and the range is y is greater than K or less than K, depending on if the graph is going up or down. So we can apply all that stuff here while recognizing that this is a less than on it. So we're going to be doing some shading. That's all that does, is throws in some shading. But I can identify, okay, a equals -2. I can write also a equals -2, h equals 1, k equals 4. Now usually the parent function does this, 0, 0, 1, 1, 4, 2. This is the graph of y equals the the square root of x. This new graph is going to start at the point 1, 4, which is here. Starts at the point 1, 4. It's going to go down 2 every time it takes a step to the right. The question becomes, where should those steps be? Like, I know I have the point 1, 4, but then I didn't know what goes here, and what goes here. What are the next 3 points that I can squeeze in here? Well, I'm going to take this, x minus 1, and set it equal to 0, 1, 4, and 9. These are the numbers I want to plug in for x. I'm going to plug in, well, add 1 to all these. 2, 5, and 10. Now the way this is set up right now, I can't fit 2, 5, and 10 into there very well, so I'm going to slide all this over. You should be doing the same thing when you're graphing. That also slides this over. I'm starting at the point 1, 4, and all this is going to come down here. Let's get rid of these now. So I'm going to plug in 2 for x. 2 minus 1 is 1. The square root of 1 is 1. Times -2 is -2, plus 4 is 2. That's the point 2, 2. 5 minus 1 is 4. Root 4 is 2. Times -2 is -4, plus 4 is 0. And yes, I did that really, really fast. Maybe you can't do it that fast. Whatever, just figure it out. Notice how these went down 2, down 2, down 2 each time. Why? Because the a value was -2. If you pick these points smartly, the graph will change by that a value. This graph will look kind of like this. The domain is the set of all x such that x is greater than or equal to 1. The range is the set of all y such that y is less than or equal to 4. And then I've got to remember that this had a less than. So I've got to pick everything that's less than this y value. This means I'm shading below. And I get to grab my fun little crayon. And when I shade below, I can't go to the left of this 1 because none of that stuff is in my domain. Looks like this. Something interesting to note. Had this been a greater than instead of a less than, had it been y is greater than -2 parentheses x minus 1 plus 4. Well, then we'd be shading above, and if we were shading above, our our range actually becomes all real numbers. Because we're graphing down, but then shading up, we cover everything. So keep that in mind. Don't spit out your domain or range till you've graphed and shaded and then check to see what the graph hits. In this case, the graph hits every y value, but only the x values that are greater than 1. As a bonus. And if that doesn't make sense, if you don't like that, fine, just plug in numbers for x. I'm going to get rid of all of this now. Just plug in numbers for x. Just make sure you don't start with 0. Start with whatever makes this equal 0. Start with plugging in a 1. These will not be whole numbers. They'll be messy, messy decimals. So fight through that. That's why it's better to be smart about the problem, but you have that option. This is our last one. We've talked before about how to simplify radicals. Root 12x, we can graph that the way it is, but 12 is 4 and 3, and 4 has a pair of 2s, and I can pull out a pair of 2s. So this is, I can think of this as f of x equals 2 root 3x. I pulled out the 2s, the pair of 2s, and the 3s stay behind. This is no longer in the AHK form. We can't trust this stuff because of this number here. There is actually a way to account for that. I've not been talking about how we could be doing b times x minus h plus k. And I'm still not going to. But the rules don't change. I'm going to plug in numbers for x such that I get 0, 1, 4, and 9. Well, those numbers are 0, 1/3, 4/3, and 9/3. And 9/3 is just 3. You go through and you divide all this by 3. So now I plug this in for x. I'll plug it into this one or this one, doesn't really matter. I'll do the bottom one just because I want to show consistently. 0 times 3 is 0. Square root of 0 times 2 is 0. This is the point 0, 0. 1/3. 1/3 times 3 is 1. Root 1 is 1 times 2 is 2. 4/3. 4/3 times 3 is 4. Root 4 is 2 times 2 is 4. And then 3. 3 times 3 is 9. Root 9 is 3. 3 times 2 is 6. Look, they all changed by the a value. Now I'm going to go to 1/3, comma 2, 4/3, comma 4, 3, comma 6. I could keep going now. So like the next perfect square of tonight is 16. So 16/3 is what? 5 1/3. And I'll go up 2 more to here. That's enough. Square root function. Domain x such that x is greater than or equal to 0. Range y such that y is greater than or equal to 0. Let's recap. A square root graph is the inverse of a quadratic. We can only grab half of it, otherwise it wouldn't form a function. So here's a quadratic, here's the inverse of it, but we just want the top half, we get rid of the bottom half. If a function fails the horizontal line test, if it isn't 1 to 1, its inverse will fail the vertical line test. It won't be a function. Square root functions are transformed with a, h, and k, just like the rest of the functions we've seen. The key here is picking smart numbers to plug in for x. Numbers that result in perfect squares like 0, 1, 4, and 9. Simplify radicals first whenever you can. Peace. Yeah, I said it.